Hello everyone, welcome back to Calculus. This time we continue work on integrals. This is the definition of integral, and be careful about the way to write a definite integral. Do not forget dx in the end, okay? And also do compare with the way how we write an indefinite integral or antiderivative. Okay, indefinite integral really follows very similar to the integral we are having here, but anyway, without the upper bound or lower bound. And also we said one explanation of an integral, it is the area underneath the graph of a function like here for O and above the x-axis for x running from A to B, for x running from A to B. And indeed, this is precisely how integral it is defined. It is the limit of the Riemann sum. And the meaning of the limit of the Riemann sum, simply it is the limit of the sum of the areas of rectangles, smaller rectangles. And also we did actually two examples. We tried to explain in a rare case, in a not very common case, okay, although I really will have to say in a relative simple case or very simple case. If you can identify the graph and if you can calculate the area directly, and then you can solve, you can find the definite integral directly in a rather easy way. But anyway, mostly it is not the case. Then the real question is, how do we evaluate a definite integral? So we are moving to 5.3, the so-called fundamental theorem of line integrals. And also, I just want you to know, if you are following the textbook, indeed on our textbook, there are two parts. And for our consideration, we are just considering the second part of the fundamental theorem part, fundamental theorem of that line, a fundamental theorem of integral. I'm sorry, this is really, it's not a line integral. Fundamental theorem of integrals, part 2. So the way to calculate a definite integral is to find out the antiderivative. I wrote well, first of all, it should be clear uppercase f and the lowercase f are different, right? And then I say the uppercase f, the derivative of the uppercase, it turns out to be the lowercase f, which really means the uppercase f, it is an antiderivative of the lowercase f. So to evaluate a definite integral, you find out the antiderivative and then take the difference of the antiderivative at the upper bound and the lower bound. That should be it. This is really the so-called fundamental theorem of line integrals. How about let's work on some examples to see if it is easy or if it is hard to understand the so-called fundamental theorem of integrals. We are having the example from the textbook. Evaluate an integral from -2 to +2 of t squared minus 4 dt. Don't forget that it's dt in the end, okay? If you have variable x, and you need to have dx in the end. If you are using variable t, you need to have dt in the end. So clearly, according to my understanding, we needed to find out the antiderivative first. In this case, it's easy enough, right? Antiderivative t squared, it's 1/3 t cubed. Antiderivative 4, that's 4t. So 1/3 t cubed minus 4t. Then, according to this so-called fundamental theorem of integrals, fundamental theorem of integrals. Okay, we use this antiderivative, the antiderivative evaluated at the upper bound and the lower bound. So at the upper bound, replace each t with 2. At the lower bound, replace each t with -2. Then you do all the calculations. Still may take a few minutes, but anyway, I just want you to know the answer should be -32/3. The answer is -32/3. An integral, in general, we can say it is an area. But anyway, you want to know an area, it is always positive. Okay, integral indeed could be positive, could be negative. And in this case, if you wonder what's the actual meaning of this negative integral, you look at the shape of the region. It turns out to be entirely below the x-axis. Okay, the region we are considering, it is below the x-axis and above the curve of the graph, the curve of the function. So the integral just turned out to be negative. The area, it is always positive. And one more example using fundamental theorem of line integrals. We are considering the definite integral from 1 to 9, x minus 1 over square root of x. According to the fundamental theorem of integrals, we need to consider the antiderivative. So this is the antiderivative work I did. Okay, look at this part. Without the upper bound and lower bound, it's the antiderivative, right? And then we understand the way to find the antiderivative. We are going to use those basic formulas like a power rule and exponential rule, logarithm, those things. And clearly there's no trigonometric function here. Okay. Speaking of power rule, don't forget square root of x is a power function when it is considered as x to the 1/2. But still keep in mind that when we find out the antiderivative, we cannot jump somewhere to the denominator or somewhere in the middle directly. So really, you want to simplify this integrand first. Square root of x, it is converted to x to the 1/2. And then the integrand can be separated into two functions, x over x to the 1/2 minus 1 over x to the 1/2. For the first fraction, indeed, it is just x to the negative 1/2, right? And for the second fraction, now I think I just needed to realize there's something wrong here. For the first expression, really, I should have x to the 1/2 because x on the top over x to the 1/2. For the second expression, I should have x to the negative 1/2, x to the negative 1/2. And then, really, the antiderivative will have to be changed accordingly. It will be like this fashion. Antiderivative of x to the 1/2, and antiderivative of x to the negative 1/2. Sorry for the mistake, I'm trying to fix it now. So then, for the first term, it really tends to be 2/3 times x to the 3/2. So let me put it in this way. And then this will be plus, because 2 minus sign, this really tends to be plus, right? Actually, this is minus. 1 over negative 1/2 plus 1 over 1/2, that's 2. But it is minus in the front there. And so this really will have to be changed accordingly. Minus. Remove that minus sign. So at least I think I got the antiderivative part fixed. And I'll double check with the textbook if I got the correction done correctly. Okay. Then, according to the fundamental theorem of calculus, basically we are going to use this part. It is, again, it is true. In the calculation of the fundamental theorem of integral calculus, really this is called the fundamental theorem of integral calculus. You don't need to consider constant. And then, I think the number, this part still should have to be corrected. This will be minus. I will double check if I get the number part correctly. I hope I did, but anyway, for now, I'm not sure because I'm also looking at making the video at the same time. And I'll double check with the numbers. I hope I get the number correctly. And indeed, I think it should be. Okay. This time, the integral does tend to be positive because the area we are looking for here, it is above the x-axis, entirely above the x-axis. Entirely above the x-axis. Okay. So this is really about the fundamental theorem of calculus. Let me double check. Fundamental theorem of integrals. Really, it is called as the fundamental theorem of calculus. We do have fundamental theorem of line integrals, but anyway, not in this calculus 1 class. For now, this is the fundamental theorem of calculus, which says to calculate a definite integral, we need to find out the antiderivative and then evaluate the antiderivative at the upper bound, at the lower bound, then take the difference. Put in a simple way, to evaluate a definite integral, you do need to know those antiderivative formulas. Antiterivatives are also called as indefinite integrals. And the integral we introduced today, it is the definite integral. So I do have those basic formulas. Copy and paste it here again, and do take a look if you feel good with all of them. Thank you for watching.